us again today after a long day yesterday. I hope everyone still remembers what we talked about yesterday, but just a quick recap of what we looked at yesterday. So, yesterday I talked about just a brief history of my studies and what I'm interested in teaching. Looked at some of the field studies I've carried out over the years in different ships. And here we explained, like the main point here is just to show things are tied down on big ships because, like once the waves start hitting, then things are moving all over the place. And I showed like a few different research vessels. Here's the Meteor from the German Ministry of Education and also Ministry of Science. And just to give an impression how big the ship is, here's also another picture, and my favorite creature, the colorless or transparent organism from the ocean we collected along the Namibian waters. Here also I try to give an impression of like the research I've done in Antarctica, just an overview of the different features how we found like ice caps and penguins, seals, and also an impression of the ship we used, an icebreaker belonging to the US Antarctic program. And here with the ship you can be out at sea for 75 days with 26 scientists. And just an impression again of what, like the different features you see. Here you have cans of soda in ice, you don't need a fridge. Also, I tried to explain what my ongoing research interests are, that is using remote sensing as a tool to study ocean plastics, so plastic litter, aggregated material that has come together. And so the observations are from ships, drones, aircrafts, and satellites. And then, of course, I gave a brief introduction to the University of Oldenburg, where I'm currently stationed. Try to give people the impression of where exactly it is, Northwest Germany, and the different institutes or facilities available at the university. And again, just a bit more on where we are doing research in the global oceans, fjords, seas, lakes, and estuarine systems. Just the education, what is being offered through the institute, the different types of resources also available at our institute, the different boats, small boats like 6.5 meters long and some of them 18.5 meters long, doing research in the coastal waters of Germany in the Badensee. And then of course, once you go out into the open ocean, we are the host institute of the Sonne, which is the German word for sun. This is a big vessel going out at sea for at least 50 days with 40 scientists and 35 crew members working 24/7. And just as an impression as well, I try to show, how big it is compared to the small boats when it's docked here. The example was in Mexico. And then just also a brief introduction of what the working group I'm part of is doing. And then, of course, one of the main points I tried to stress yesterday was why we do environmental measurements, or why we are doing measurements at sea or in the environment. We collect data. The data we use to confirm what theory is telling us, and then we have numerical models that help us get a better understanding of what the data and theory is telling us, and then we can fortunately we can easily do predictions. This where I asked a question, please. Different ocean properties, the chemical, biological, optical, geological, and physical parameters. And of course, one thing I just have to stress is whenever you're going out to do experiments or you're going out at sea, there is a lot of planning. So there's always the who, what, where, when, why, and how. So here, I don't know if there are any questions, but this is the schematic that just, if you can use this as one of the ways to study, to prepare your field work, or if you're going to do any experiment, the who, what, where, when, why, and how. These are the main basic questions you always have to ask yourself. And at the end of the day, it's, why. Also, I try to explain to people, like when you're doing mostly oceanics studies, you have a map of locations where you're going to study and the grid, and you try to have a daily plan of activities, what you're going to do, what is going to happen. And here I also try to stress the point that at any given time when you're doing experiments, you do one activity at a time on a boat. The main reason being that you can, whenever anything goes wrong, it's easier to manage compared to when people are doing different activities at the same time. Then if something goes wrong, then it's always difficult to coordinate the people and also the crew to figure out what is wrong and how to resolve the problem. And here I also try to present, like a sample data sheet where you collect data. The most important things, it's always the time, the location, and other parameters that you can record at a given location. So sky cover, angle of the sun, wind speed, water depth, and these might be important, like for people who are looking at, if you're going to do sediment cores, you need to know how deep you are going to deploy your instruments, and also other parameters like circuit disk depth and Forel Euler. So today I managed to bring one of the scales. I'll try to explain it later. Then I gave a brief history on oceanic surveys, the first recorded long surveys that were conducted in the 1800s, like 1873, by using the HMS Challenger, and this was by Sir Thomson. And then I gave, like a summary of what happened during those cruises, how far they traveled, and the number of different species they discovered. And then, of course, I gave also a brief history on instrumentation that were used during those the HMS Challenger cruise, and an overview of the different discoveries or proposals that were made by different scientists over time. The continental drift by Alfred Wegener in the 1920s, and then of course the plate tectonics around the 1965s. And then also you have to understand that most of the oceanic studies were also motivated, or the technology was motivated by military activities. So the Navy, the need to travel to different locations. Well, I remember I was talking about spying, but I'm not sure if that's the right word, but yeah. Then here we talked about operational oceanography, what is actually happening when you're doing operational oceanography, and how it's important in the community for everyone, like citizens and different entities. Because once you collect data, you know what might happen in the future, and you can at least warn people before things happen. So, for example, floods or earthquakes. So the instrumentation we have that is out at sea or even on land is useful for us to warn people of forthcoming activities or extreme weather conditions. So that's the ability to be able to timely provide information to citizens or government agencies or policy makers. And then I talked about the Global Ocean Observing System that try to coordinate activities in the ocean, like different measurements, how things are done, ocean best practices. And here, just the main thing, I try to give a definition of operational oceanography. That is the activity of systematic and long-term routine measurements. And of course, once you have your measurements, you have information, you have to pass it on to people or to different entities interested in the information. So you can do nowcasting, forecasting, and hindcasting. And a nice schematic of what hindcast, nowcast, and forecast is about is hindcast. You're looking at previous measurements, long-term series that have been conducted over the years, so you can understand what the weather or what the conditions were like. For example, I gave the example yesterday, if you're going to do hindcast, it's something that happened before, so it's either in a couple of years ago or a few hours ago or a few days ago. So for the example from yesterday, we had 18 October 2021 as the nowcast measurements from that time, and then hindcast, I gave the example of 1980, and then forecast something in the future. I gave the example of 18 October 2050. And then I spoke about different entities and how the components of GIS are structured, and then different entities that are dealing with different parts of the oceans in different regions. Here was an example of the different in situ elements that are within the global ocean observing system. Here you have argo floats, deep argo floats, bio argo floats, moored buoys, tsunami meters. You have platforms, you have ghost ships, you have ice buoys, you have fixed platforms, you have surface drifters. You also have like automated platforms, you have radiosondes and XBTs. These are like simple handheld CTD meters. And then here I gave an example of the Ocean Observing Network in Germany, where you have different platforms, technologies. You have the inclusion of use of satellites to communicate data or to collect data. You have seabeds used for tracking. It could be water surface properties, or even tracking the seabeds themselves, trying to figure out, like for people who are interested in beds, trying to understand where beds are going and like if they are moving at a certain time or what is affecting or motivating their movements. You have ship-based ferry boxes. These are sensor boxes where you can measure things underway when the ship is moving. You don't really need to control them. They are automated, autonomous. And you have research vessels that are dedicated to research. You have instruments like gliders that are moving within the water column. They go in any direction. You tell them what to do, and whenever you want data, they can always deploy the data. So they're operating on batteries. And then you have underwater nodes. You have the coastal research area where things are coordinated from. So I also gave the introduction to the measuring platform that is run by the University of Oldenburg, where we have different instrumentation in the water column and above the water column, and measurements are collected from 1 minute to 15 minutes, but this is continuous, and this has been going on since 2002. Here, just to give an impression of like the measuring platform, and the one of the university-owned boats, where technicians try to go to the station every 2 weeks to clean or service instrumentation if in case something is going wrong or something is working, just to make sure things are smooth. Here I also tried to explain the different parameters that are being collected at the station. You have salinity, temperature, pressure, nutrients, fluorescence, current velocity. And if you go on our university website, you can actually observe measurements as they are collected, so in real time. And in some cases, you also have a time series to see data from before, so hind casting and now casting. And then you can use that data. So for example, here, we explain the applications of the data that is currently being collected. So that's the investigation of processes, like different biological, chemical, and physical processes happening in the Wadden Sea. So all the data collected here has been used in some way or the other way to do modeling studies, so to be able to forecast, right? So in the models, you do hindcasting. That's where you have data. You do your validation, verification, if what your model is telling you is the same as what was actually measured. And then you can, if you have that accuracy, you can start to do forecasting, trying to figure out what would happen in 2 weeks' time, in 3 weeks' time, in 3 years' time, or 10 years' time. And then developing and testing new approaches to investigate water parameters. Here, that's one of the applications of the station. And then here, I try to give an overview of different instrumentation. Here is a CTD that is used in the open ocean. And then you have a rosette, different water sampling bottles here. And this allows you to collect water at different water depth. And then you have a sensor here providing you temperature and salinity observations. And here also dissolved oxygen sensor that is located here. Here, just an impression of how things can be out at sea. You have high waves, and that's why you also have to tie down things. And then, of course, the labeling of water bottles, so that you know, like, you collected water bottle number 1 at a certain depth. For example, if you do it in a chronological way, let's say 1 is the deepest, so you collected water from 200 meters. So your bottle 1 and 2 would have water samples from 200 meters. So going on, 3 and 4 would have maybe water samples from 150 meter water depth. And here you just have 2 people trying to make sure the CTD, once it's lifted by a crane, just try to guide it into the water column, just to avoid if it is swinging. As you know, like if you can see there are high waves, sometimes things can be moving randomly, and that's always good to just hold things safely. Here I also tried to show an example of mood sediment, like sediment traps. This you can either have it floating so that you collect material which is within the water column, or you can have something that is drifting, moving up and down, or you can have it stay like fixed to the bottom of the ocean. Here example as well here shown here. And here's an example of one which is floating in the water column. Here you see the buoys that will help it float within the water column, and then sediment collection will be done here this, from the top, going into the water bottles. And also you have to label things to know where you collected your samples from, and the location, time, and dates. Here also I try to show examples of plankton nets. You want to collect microorganisms in the water column. And then different sensors, temperature sensor here, bathythermometer. Here it was used to measure temperature and also try to understand sea visibility in the old times. I also showed a Secchi disk depth, which is a measure of water clarity. It's used to measure water clarity. Try to explain here what Secchi disk depth is, or how you look at it. I'll try to explain that in today's main lecture. So that's just an overview. Turbidity meter, trying to measure how much material, like scattering material, is in the water column that is dissolved and dissolved material, and organic or inorganic material that can only scatter light. And here, one thing, the message was to say it's quite difficult to intercompare measurements from different instruments, so you have to make sure you understand how the instrument is measuring turbidity. So here, it's just a summary of how the different instruments measure the turbidity. Here you have 90 degrees to the incident light, and here sometimes you have other sensors that have 30 plus minus 15 to incident light to the backscatter. And then here you have 180 to incident. So different instruments, different measurements, different parameters. So always be careful when you're looking at turbidity measurements from different instruments. Always check the units and try to understand how the measurements are actually being collected. And one thing I try to also explain is instrumentation. That is, in the water column for a long time you have problems with biofouling. How do you define the color of water? There is a standard approach, the Furore-Ule scale. I will try to explain more today on this. And just a bit on ocean color remote sensing, using the information collected from light in the visible wavelength. And then just also an impression of like trying to collect measurements at sea of light using radiometers, and absorption and scattering instrumentation, which I'll try to explain today. Then also other instrumentation, acoustic Doppler current profiler, that is used mostly measure the velocity in the ocean. Here try to explain the idea behind the Doppler effect, Doppler shift. That's when a train is approaching, you have higher pitch. Then when it's moving away from you, you have a lower pitch. We'll continue. So we were talking about ADCP, different sensor setup for the different applications. Here I gave an example of an AUV, autonomous underwater vehicle. These are also programmable. You tell it when to move, where to move, and you can put a number of sensors. So like Lego, you can always put modular. So it's modular. You can always fit different sensors as you feel you want to do your observations. So here you see there's an example here. It's combining a transducer. You have a DCP. You have a camera system. You have here also a camera system at the front. You have let's see what else is connected here. Yeah, I think that's some, but you can add other instrumentation as you see fit here. Okay, so just other extra examples, additional examples. Here's an example of an Argo float. In most cases, Argo floats, you have them measuring temperature and salinity. And they can move up, sideways, up and down, sideways, up. So for this example, it moves up to communicate data, and then after a cycle, at some point in time, the battery will die. So in most cases, you program it to be floating by the time the battery is close to dying. Right. Then here is just an understanding, like an impression. This is from 2017, but I guess there are latest versions. I was talking about Argo floats. Here is just a map. This is from 2017, but of course we are in 2021. The number should have significantly increased. Different countries, different number of Argo floats out at sea. And here I was just showing off some of the activities conducted by the Marum here in Germany. Or using the ship Meteor, they discovered some hydrothermal vents, and they had a submersible here in the middle. Let's see if I can use my pointer here in the middle. And then here I was showing off like some of the other instruments, seismic sensors, gliders, tide gauge, Mockness nest, where you can collect plankton samples from different water depth. And here's just an example of the Mockness nest being used here. Collection of the samples here at the bottom. Let's see if I can use my pointer again. Here you have the collectors at the bottom of the Mockness nest, and magnetometer, ocean bottom seismometer, and then here's an example of Alvin, a 3-person submersible that managed to dive up to 4.5 kilometers into the sea surface. And in 1977, there was the discovery of hydrothermal vents where temperatures can be up to 1,200 degrees Celsius. And yeah, just a few links for those who are interested. Technologies for observing the ocean. You have geostationary, like satellite server, remote sensing satellite imagery. You can also observe them from NOAA. You have the NGDC site. Floating devices in the ocean. You can look at the Argo Float website at the University of California in San Diego. Drifter program, you can also have a look at the NOAA program. Submarines, here you can go to the Ocean Explorer. And automated underwater vehicles, here's just an example. So I'll give you a minute to have a look at the links. If you want to note them down, then I'll go to today's lecture. I hope if you are coping, you manage. Okay, thank you. Then, today's lecture. So today we are going to look at remote sensing. So this is more like my specialty. This was what I was supposed to do to start with the recap, but I hope now you have an idea about why we study the ocean, what is operational oceanography, what are ocean properties, what platforms are used to study the ocean, what instruments are used to measure the ocean properties. Again, so yeah, this was supposed to be the recap, but anyway, there's no harm in repeating things, I hope. So we collect data to confirm or verify what theory is telling us. You put that into models. We have a better understanding where we have data, theory, numerical models, and then we can do predictions. And so there's always a question like, why do we really care about the oceans? Why do we study the oceans, right? It's because everything is connected. So the climate system connects everything on planet Earth. The oceans cover 70% of the Earth's surface, and the land we are saying like, 28 to 30%. And of course, with sea level rising, then of course those numbers are slowly changing. But if you look at this figure, let's take a minute to really understand this figure. Everything is connected. So you have solar radiation that influences precipitation, you have back radiation, you have evaporation, which contributes to sea level changes, well, to some extent. And when you have more rain, you have weathering, you have land being moved, like sediments or solids being moved into the ocean, you have runoff. And if you have trees, then water can sink into the water column. You have tectonic activities where the ocean, in the mid-oceanic ridges, the ocean is spreading through to internal volcanic activities. You have deep water, you have carbon production, you have upwelling, you have carbon burial, you have winds moving gases from volcanoes on land. So the main message is everything on the planet Earth is connected. So the climate system is connected. You have greenhouse gases, where if you have the ozone layer being depleted, you have more radiation coming in. That means more droughts. You have more, warming up of ice sheets. So you have plate movement. So things are connected. I guess the main message is just to let people know things are connected. So here, just at the bottom, you see different latitudes from zero, like from the equator, where we are close. Yeah, Uganda is close to the equator, and 90 degrees, like the polar region. So this applies North Pole, South Pole. Any questions about this? Or make sense? Any questions in the chat? Or people understand this very clearly? My example is very excellent. People are happy. No questions? No questions? Okay, good. Well, yeah, so I have to bring this again, planning, and yeah, taking things, noting things down and planning ahead when you do field work. Again, nowcasting, forecasting, hindcasting, the example I provided yesterday. So nowcasting, like now, today, real time, near real time, and then hindcasting, looking backwards in time, forecasting, looking into the future. So again, looking at this example, you have data helps you verify theory, and you apply that into numerical models using hindcasting data and nowcasting data. Then you can do predictions to do forecasting. So today's agenda, the main agenda for today, we are going to cover aspects of remote sensing. So what is marine optics? What platforms can you perform remote sensing? How do you determine ocean color, the color of the ocean? And a recap and deep understanding of tools that we discussed yesterday. So one of the main tools we discussed, briefly looked at, was the Fourier-Euler scale. Can we show it shortly to people? Here. So that's the scale of the different different colors of the ocean we expect to see. Well, of course, you have other colors in between, but these are the main primary colors you'd observe at sea. And you have numbers here, like to identify the different colors, 1 being the bluest ocean waters, and then 21 being the darkest dark waters. And then, of course, we have other instruments. I'll show you again once we get to that part of the lecture, but yeah. Anyway, so what is marine optics? So marine optics is one component within physics, where you look at marine physics, you look at all these components, they join together. So, like marine physics, marine biology, marine chemistry. So within marine physics, we have marine optics, where we look at information from the electromagnetic waves. So for us, of most interest, like when you're looking at ocean color, what is contributing to the color of the ocean, that is in the visible waveband from blue to red. So the main properties you're looking at are absorption, light being being taken in by an element or material, scattering, like bouncing back of light either forward or backwards, fluorescence, like excitation and emission of light at the different wavelengths, radiometric quantities, which we'll be measuring with the instruments I'll show you. And then you have within a topic of environmental optics, that's where you have hydrological optics, ocean optics, coastal optics. Any questions about this slide, or everyone is fine with that? Any comments in the? Okay, people understood it, great. Yeah, so one of the examples I was just showing you, the Secchi disk depth. The first measurements were recorded in 1815, like the well-known measurements were collected by a German naturalist, Albert von Chamisso, did measurements during like the Russian Rurik expedition under the command of Otto von Kotzenbuer. So if you see the dates, you can imagine like measurements of using the Secchi disk have been going on over centuries, right? And NODC has one of the largest data sets, over 400,000 measurements, and the number continues to grow, and these measurements have been collected across the globe, like in different locations for over 100 years. So a nice introduction to this, if you are really interested, I think it's a nice read. It's a paper by Marcel Venand. It's on the history of Secchi disk. So if you just Google this, you should be able to find it. It gives you a nice impression of what really is the Secchi disk and what is the history behind it, how it, more or less like it started and where we are today in terms of Secchi disk measurements. And just to give you a nice example or like impression, so this is one of the examples, like one of the Secchi disks, like one of the first ones from 1890, and then you see like what we have nowadays. So they are either made out of metal, you can have a metal plate measuring 20 centimeters diameter to 50 centimeters, or you can make it out of plastic. So this is a plastic example, and this is a metal example. And here, just to show something that happened recently, we had an experiment in Lake Victoria. So here you can see example of I would say expert scientists showing off, like trying to get measurements of Secchi disk depth and color measurements in this example. So how do you really take Secchi disk depth? So so the question is, what is Secchi disk depth, right? SDD. In some papers or in some presentations, you'll notice some people just give the abbreviation SDD. So that is the distance at which the disk is no longer visible as measured from the water surface. So in this picture here, you see one of our trained scientists also trying to take the measurements of like the Secchi disk depth at one of the stations during the survey in Lake Victoria recently in October. And if you look at this example here, where the schematic from this paper from Bruin et al. 2019, when you first lower the disk, you see it's very bright, and slowly you end up losing visibility where you can't see it anymore. So in essence, the total distance is the distance from you, the observer. You could be standing on the side of a lake, or like you're on a pier, or you're actually on a boat. So most of these measurements are done from a boat, but you can also do them standing near the shoreline if you have a pier or some point where it's safe to do these measurements, right? And so you have your total distance. That's the distance from you, the observer, here where you're holding the Secchi disk. And here in most cases, it's easier to do it with a tape measure where you can actually see the numbers, but sometimes you have a rope where you mark the distances, maybe in 10 centimeter steps, 20 centimeter steps, depending on the location where you're doing your experiments. And then, so you have the total distance that is from you, the observer, and then you have the distance from the observer. So you know the distance from your boat to the water surface. So to calculate the Secchi disk depth, that is just the difference, the total distance, and your distance from the observer. Any questions about this, or I'll give people a second or two to carefully scrutinize the image and like the approach here. I'll give you, maybe a minute to carefully look at this whole setup and how you do. If any questions, please just type them in the comments. No questions? Everyone happy? No questions? Yeah, I'll just give people a minute to. Yeah, it seems it's straightforward, wonderful, great. What a great audience, thank you. 3 minutes. We have a small quiz. Again, have a look at this image, right? The circuit disk depth is a measure of how much material is in the water, right? So that means the more material, then the less the depth is going to be. The less material, the bigger or the deeper you can observe the disk from. So here, I have a question for everyone. What is the right relationship of the circuit disk depth and the material concentration in the water column? So here you have the circuit disk depth on your y-axis, and on your x-axis you have particulate and dissolved materials, the amount of material in the water column. So it's either low, it's high. So when it's low, does it mean like when it's low, the circuit disk is also low, and then when it's high, it's also high. So that's the relationship indicated by B. Please type your answers, and then if your circuit disk depth, like it's very deep, then you have low material. If it's very high, then you have high concentration of material. Does it make sense? So the question is, which relationship is correct here? What would you expect with the circuit disk depth? Like, would it be this relationship where if it's very deep, then you have less material in the water? If it's very low, then you have high concentration of material? Or is this relationship correct? Like, it's the same, like when it's low, the circuit disk is also low. When you have more material, then it's also deep. So a negative or indirect relationship, or is it a positive direct relationship? I give you, I say 3 minutes. So type your answers, then we'll see. How do I see the answers? I have to see the answers. We have to see what people are answering, A, B. So there are two possible answers, A or B. Nothing is wrong, but well, something is not acceptable. Okay. All right. There's a question, how is subjectivity for the ST? Well, I'm not, what's happening? Huh? When it says connecting, is it okay? It kicked me out anyway. So 3 minutes. Again, as a hint to the answer, look at this figure again. If you have the disk, as you are putting it within the water column, its visibility, the depth at which you observe it, depends on the amount of material in the water column. The more material you have, you are likely to have a lower depth where you lose it. Like in the surface waters, you probably don't see it anymore. But if you have less material in the water, then of course you might go even up to 200 meters, right? So my question is, low material, low circuit depth, which is the relationship you see in B, do you expect it to be B? Or do you expect it to be A, whereby less material, you can see up to deeper waters? High material, more material, you can see only just surface waters. How many answers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have more people in the room. They should answer. 3 minutes. We have 1 more minute. Interesting answers? All right. So I guess I can. Are we ready for the answer? Okay. So the right answer, the most appropriate answer, is the relationship A. So again, look at this. Remember, you have high Secchi disk depth, that is, you can see up to deeper waters, or you have very high water clarity when you have less material in the water column. So dissolved and particulate material, if you have very few of it, then you can see up to it depends with the location. In some, in the open ocean, up to 200 meters, 300 meters. Maybe 300, I'm exaggerating. As long as you have a disk that big enough for you to see all the way down, but in most cases, 50 meters, you can still see a disk in some cases if you have very clear water. But then as you see, so here, as you add more material which is dissolved and particulate, that's when the depth is low. So you have a low Secchi disk depth and low water clarity when you have more material in the water. Does this make sense? Or any questions about that? Well, I guess people understood it, no questions about it. Wonderful. So, high Secchi disk depth, very high water clarity, low water clarity, low Secchi disk depth, more material in the water, less material in the water. Yeah? Okay. So, there's a question? Oh, okay. It just makes sense. Okay. So, over the years, we have done some studies where. Are you okay? Are you okay? Okay. Okay. Yeah. Sorry, there was a glitch in the power, but anyway, everyone is still connected. We have looked at the study where also the Secchi disk depth, we have tried to do a correlation with chlorophyll, and over the years there are studies that have shown there is a nice correlation because, of course, chlorophyll, the algae material, also contributes to some of the dissolved and particulate material in the water. Well, of course, whenever it's dying down, when it degrades, then it becomes like some of the dissolved material. And then, of course, if it's still living, then it's particulate material. So there's a nice correlation if you do a non-linear fit. You will find out that the Secchi disk depth is related to chlorophyll. So here are the different fits, like from our study. And from different studies, like they've proposed different algorithms to show that you can relate chlorophyll and Secchi disk depth. Similar color, the color of the water also is related to chlorophyll. Like I'll try to show that again. But here's an example from a different study where you see the nice fits, nonlinear fits, exponential fit here, and from another study that was done in Greenland. Any questions about that yet? Well, everyone is okay with that? I hope so. Okay. So just to show you some studies where they've been nice correlations and they've collected data where they show that the Secchi disk depth here, so that's ZD, represents the Secchi disk, the depth of the Secchi disk, has been shown to be useful. You can, with this model, you can try to estimate chlorophyll. And here is also another study from 1989. This is from 1992, and then 1977. So all these different studies and all the number of measurements they have shown, there's a nice correlation between Secchi disk depth and then chlorophyll A. So chlorophyll A, the algae, the primary producer of the primary producer in the ocean. Any questions about this relationship, or it's clear for everyone? Okay, so there's always a question like with the class. So we are still dealing with the classical tools, and I was showing you the Furore color scale, the one which has like 21 classifications of water color. And the main question is always like, why does the ocean look blue? Why is it green? Sometimes why is it brownish? The simplest and simplified answer is because of the material in the water. So you have suspended mineral solids, you have phytoplankton, chlorophyll, which is chlorophyll A, measured as chlorophyll A, or color dissolved organic matter. So what happens? They absorb the light, they take in the light, or the particulate material, it scatters the light, it moves it in different directions, right? And of course, the water itself contributes to the absorption and scattering of light. And one thing that is very important to note, the color of the water also depends on your perception, like the human eye. Some people are colorblind, they don't see the color blue properly, or they don't see the color green properly. That's why it's human eye color perception. And of course, you have the environmental conditions that contribute to the color that is visible at a given time. And then you have the water constituents, which is the parameters or the constituents in the water or the properties in the water, that is chlorophyll, color dissolved organic material, suspended mineral solids. So that can be sediments, could be silt, could be clay, or whatever type of sediments you have for any region. Make sense? Or any questions about this slide on apparent color of water? No questions? Everyone understood? No? Good. So going back to, again, to looking at color, there are different other systems. Here I give the example of the Foro-Euler color scale system, and there's another one called Mansell color system, but not so many people are using this. But in this presentation, I'll concentrate more on the Foro-Euler color scale. So as you can see, this is a wooden example or design that was proposed in the 1930s or 1950s. And this is something that was also proposed in the 1895, or published in 1895. So this is mostly the open ocean where you have the blue waters and slightly greenish waters, right? And here, just to give you an impression, we have one of our trained scientists looking at the color using a Foro-Euler scale, like the one I've just been showing before. This is the difference. So you see the difference, this is what we are using now in 2021, and this is what was proposed in the 1930s and 1950s, right? So here's a study, you can also try to maybe estimate the color of Lake Victoria from the picture, but you might, I guess, maybe I'll give people 1 minute to to say what color the scale, you cannot see it, so it's difficult. Anyway, it would have been nice to put the scale and then have people try to guess what color the Lake Victoria was presenting on this day. So, how do you measure water color? What is the best way to do it? Recommended way? So it's always difficult. Best way, recommend. I would say the recommended way to do it when you're on a boat. Here, just for illustration, we were taking measurement in the sun, and then of course you have the problem here when you're measuring at the equator, the sun is overhead, so it's difficult to get a shadow side. But ideally, you should do it in a shadow. Remember taking your Secchi disk depth. You've taken your measurement of a Secchi disk depth. You say, for example, your depth is 2 meters. So you take the disk to half of that distance, and then you try to overlay the scale. As you can see here, our trained scientists trying to get some measurements of color in Lake Victoria. You try to put it over the Secchi disk, and then try to look at the white part of the disk and try to match the color in between. Try to match the different colors. What you see here on the scale, try to match it to what the water looks like using the white background as your reflecting part, right? I'll give you 1 minute to carefully look at what is actually going on. So half Secchi disk depth, and then you try to put your color scale in between. So you can either have a scale like this, or you have a secular scale. The different scales have been developed over the years, but this is the basic one. But some people have also tried to do low cost versions of the scale. Here's an example. So I'll give you a minute to carefully look at what the scientists are doing in this example. You have your Secchi disk depth. You try to put the scale on top of this, the view you have with the Secchi disk, and then try to match the colors you have there on the scale. I'll give you a minute to have a look. Any questions about this? So remember the Secchi disk depth you measure here, that is the distance, the total distance from you on the ship, and the total distance, the distance from you measuring to the sea surface. And then you take half of that, that's where you take your color measurements. Any questions? We have a question? Yep. Wonderful. There was a question in the chat. Is there any precaution that can be taken to reduce errors? Yeah, so that's a very good question. The question is, are there any precautions? Well, as scientists, we do our best. You always try to do things as accurate as possible. So whenever you lower the disk, you try to pull it up and down to make sure, your Secchi disk depth is a good measurement. You pull it up, pull it down, then you try to figure out exact. So these are, although they are not exact measurements, because it's always, things are moving, the boat is moving, so of course your Secchi disk depth, the depth at which the water surface is, might slightly change, maybe 1 centimeter, 2 centimeters, but you have, as you can see, over the years, the numbers match. Looking at chlorophyll, you put it against transparency, they match. So the point is, I guess, you do your best to take your measurements as recommended, and then, of course, you have some room for error. So to minimize the errors, you can have 2 or 3 people do the same measurement, and then you average the measurements. That's also one way to minimize the range of error or uncertainties. You're looking at the color, so going back to the different colors of different water bodies, just a few examples. So here's a nice example that shows you some of the extreme scenarios. This was from a cruise in the Pacific Ocean in January 2018. You can see how very blue the water is. That's very blue. And then you have here from an experiment we just did on Lake Victoria in October 2021. You see an algal bloom where you see well, I don't know if it's really that visible, but if you look closely, there are lines that are the different species that are accumulating in what could be minor windrows, just specific lines. And here's another example of the color of the water. Here's in Germany, just in the port, where you see the soil. When the ship is moving, it resuspends material, and you have a very dark water color. And it's blackish waters. And then here's an example of a bloom where it's greenish, very greenish water. So I think it's a similar, well, I'm not sure of the species, but this should be Nodularia spumigena. And well, it's in the same family of cyanobacteria that you see here. Here the species I'm not really sure of, but so again, maybe this needs I don't know, 5 minutes or so. It's a small quiz again. The question here is, which one would you expect to be the right? So there are 2 answers. A, meaning 1 is the open ocean, and 2 is the coastal waters. Remember, we talked about the colors. The Secchi disk depth is when you have more material in the water, right? Material that is dissolved and particulate. And, well, the question is, look at the table and see the schematic, what it explains, and then try to see which one is the open ocean or is the coastal waters. So what is happening? So is it the case that this is the open ocean, and when you're moving, you're going towards, like the coastal waters? So as you're moving from the open ocean, is the color of the water going to be expected to be blue? And do you expect to have improving water transparency? And is it going to be the case that from the open ocean to coastal waters, you have salting of fresh water and depletion of sedum, which is something I will explain. But the main important points here: do you expect water to be blue as you are going from the open ocean to land? And do you expect Secchi disk depth to be improving as you are going towards coastal waters? Or is the other way around, like when you're going to the open ocean, you have more bluer waters, you expect your Secchi disk to be also very high towards the open ocean? So either your answer is A or B, or if you have any questions, I can try to explain the question clearly, but maybe type your answers, A or B. Have a look carefully before you answer, and then try to include your answers here. So the question is, do you expect that if you assume your answer is B, that means 2 is the open ocean. If you're coming from the open ocean, does it mean that you're improving water transparency and the waters are expected to be blue? Or is it the other way around, that you expect darker waters as you're moving towards land? That is the main question. Please type your answers. Let's see if people understand what we have been discussing in terms of color. I'll go back again so that people understand. So this is in a lake, that is a bloom. This is the Pacific Ocean. This is a bloom in a lake. Atlantic Ocean, North Sea, the coastline, North Sea algal bloom, Wadden, a lake with dead organic material. Let's see other examples we had before. So remember again, high Secchi disk depth, water clarity, that means you have less material in the water. Low Secchi disk, SDD, low clarity, you have more material in the water. And that means, again. So the question is, what do you expect? This to be the open ocean, number 2, or number 1 is the open ocean? How many people have answered? Let's see, 1, 2, 3, 4, 5. I think we have more people. I'll wait maybe a minute for more people to answer. Oh, 37, oh, we need more answers. A few more answers. There's no wrong answer, there's just an appropriate answer or reasonable answer. Okay, let's see how many people have answered. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 13, 14 people have only answered out of 37. At least get to half. All right, 30 more seconds, then we continue. Okay, it seems everyone is saying 1 is the open ocean and 2 is the coastal waters. So here is the reasonable and appropriate answer. So the case is, right, the open ocean, coastal shelf sea, as you are moving from the open ocean, your colors are changing from the bluish colors to the greenish, and then you go to the brownish waters. Why? Because you have production of dissolved organic material, that is dead material coming from plants or even chlorophyll. And you have also like concentration of algae material within the coastal waters because you have minerals and food for the algae to feed on. And then when you're also moving from the open ocean, you have a decrease or dilution of seawater by fresh water. So you have fresh water starting from like rivers and from mountains, and then you have diminishing water transparency. So the more material you have, like dissolved organic material, particulate material, the Secchi disk depth is likely to be very low. And your colors, the numbers, of course, you see like, well, it's increasing, the numbers. So it's a scale of 1 to 21. So the numbers are increasing towards 21, which is the darker waters, right? And then as you are moving away from the coastline, ideally, you have less dark waters. You are moving from dark waters to bluer ocean waters, right? Make sense? You have salting of fresh water. The fresh water is now mixing with more seawater, and the more seawater you have, you end up with more saline water. And because you have less material in the water column that is interacting with light, your transparency is higher, and you have bluing of watercolor. So just to give you an impression, this is open ocean. Again, remember Atlantic Ocean, Pacific Ocean, blue, mostly like towards blue waters. Then of course with blooms you have green waters. And then in the Wadden Sea or coastline areas you have dark waters, brownish waters. And then one other example here, you have like blackish or dark waters, like from greenish to dark waters, right? Any questions about this schematic? Or everyone understands it and it's quite clear? And that's why you also see the relationship. You remember we were talking about this relationship where you have the color index, like the bluer waters, you have less chlorophyll. You expect to have less chlorophyll. And then once you are starting to move like to the greenish waters, you have higher concentrations of chlorophyll, right? Same thing, Secchi disk depth, where you have very high, like where you can see very deep into the water column, you expect to find less chlorophyll in the water. But then if you have more material in the water, you have less clarity in terms of like how far you can see within the water column. So higher chlorophyll concentration, lower Secchi disk depth, higher Secchi disk depth, lower concentration of chlorophyll. Bluer waters, less concentration of chlorophyll. Greenish waters, you expect to have more concentration of chlorophyll or algae. Hope that's clear, or if there are questions. Okay, that's good. Okay, so this is apparent color of water, classical tools. Now we're looking at another type of classification that has been proposed in literature. So there is always, if you are doing ocean color, you will hear people talking about case 1, case 2. So case 2, that is the waters, like mostly in coastal waters where you have more material. You remember we were talking about the material that is either dissolved or particulate. So in case 1 waters, these are the open ocean, and in some cases you have beach areas where you have blue waters, like very clear waters. So case 1 scenarios, that is waters where the most material that is going to contribute to the color is either phytoplankton, its concentration, if it's more or not. Like here you have the greenish waters, you'd expect to have more levels of phytoplankton, and water itself. So the examples, open ocean and beaches, right? And then you have the case 2 scenario, that is the dark waters or optically complex waters. That's where you have the optical properties that are influenced by material in the water that is dissolved or particulate. So that's, examples of rivers, coastal regions. Does that make sense? Or any questions about this? Great audience. People are very good. So there's always a question like, why do we really do remote sensing? Well, why do we do science? That's always one of those questions that are difficult to answer, but I guess why we do remote sensing, I guess the simplest or most appropriate answer is it's a non-invasive approach. So non-invasive, it means you don't necessarily have to be in contact with the material you're measuring. So if we are looking at the ocean, you can get information about the ocean from an instrument that is in space. So here, that's why I have this similar example from yesterday. We get measurements about the water column or like the surface waters from instruments that are either on ships or on satellites or on planes, but we don't necessarily have to be in contact with the water column. We don't have to disturb the environment. So example is there are coral reefs. We can study corals from space, from planes, from drones, and using light information. But then that means all these measurements we do related to ocean color remote sensing have to be done during daylight because we depend on the sun as our source of light. And then we have already, like over the years, like since maybe the last 3 decades, we have developed instrumentation that is robust and can be used over and over again. So this is a well-established approach to study the environment, right? And one other very distinct thing is from aeroplanes or from satellite instruments, we get a wide area coverage. So that is very important. So imagine how many stations or how much area you can cover if you are using a small, well, even a big ship. The time you need and the resources required to cover, maybe, I don't know, it's just imagine the number of stations or the area in size you can cover from a boat compared to a satellite which is in space, or from a plane which is moving at 400 meters an hour per second, or it depends the speed at which the plane is moving, but you can cover larger areas over time. And with satellites, you can do it over and over again. So some satellites, they collect data in one location every day. Or some are geostationary, they are just looking at one point at all times, so you get data every hour for maybe 10 images every hour or every 2 hours. So the advantage of remote sensing, wide geospatial coverage, you can do measurements repeated, you have a non-invasive way to study the environment. So when we are talking of ocean color remote sensing, in most cases, when it comes to things that contribute, elements that contribute to the color of the ocean, that is mostly in the visible spectrum, which I have highlighted here. So the visible, from the ultraviolet, blue, cyan, green colors, yellow, orange, red region, right? Of course, some people are measuring in the shortwave infrared or the near infrared or in the deep ultra infrared. So, but the main activities in terms of ocean color, they are in the visible spectrum. So if you look at most publications or research that has been done, it's from 400 to 700 nanometers. Then, of course, as I explained, it can be below or above these wavelength ranges. Here, just an impression of the different parts of the electromagnetic wave. So radio waves, you have microwaves, you have infrared, you have ultraviolet, you have X-rays. So here, just some impressions of you to understand the different parts of the So you have radio waves here, and then you have cell phones here, and then you have microwave. You have infrared, visible for the human eye. Yeah, okay. Any questions here, or that's quite clear? Okay, good. The other reason when you are doing remote sensing, you have to know about trade-offs, right? So when you are going to start to look at things from above the sea surface, from a ship, going onto a drone, going onto an aircraft, or going onto a satellite, there are things you have to consider. Are you interested in covering a large area or the amount of information you really want? So looking at this properly, so here on the, to my left, as you go into space, you have few in situ data points, right? Measurements like water samples, you can hardly get data points from a satellite. You get mostly qualitative information and proxy info. You don't get quantitative. You cannot get really quantitative information about parameters. Let's say you want to measure salinity, you cannot really get a very high accurate measurements of salinity from space, but you can get a proxy value of salinity, right? So if you want to identify different species of, example, cyanobacteria, it's easier and you get more information if you get actual water samples. But then the number of samples are very low, or the coverage is very, very low. But once you go into space, you have a high spatial coverage. So the number of information, like the amount of data points you get, are larger when you have observations from space. But then, of course, if you're getting, like if you're on a ship, you're getting data points from water samples, then of course you are limited to the number of sampling points you can collect. So when you're looking at in situ data points, you have many of them when you're here on the ground. But then these are, you can also have qualitative, proxy, and quantitative information for analysis, right? But then here, the most you can do when you're working with remote sensing, that is mostly qualitative and proxy, like using algorithms to resolve information. There's a question? Question. Wonderful. So the question is, please clarify when studying ocean color of lakes and rivers, what is the average depth that we consider? Does it vary, or you have a standard depth we assess from? So that's a wonderful question, Brian. The remote sensing, you get information from the surface layers. What does it mean? Surface layers, it's also depending on water clarity. So if you remember we talked about this, I'll show you this example. Here, if you're going to be in the open ocean, you average information from a very long water depth where light can penetrate. So the sensor in space will measure what is being reflected from the ocean. What is being reflected also depends on the water clarity. So if the waters are very concentrated with different materials, then of course the information you're going to get would be from the very top layer of the water layer, which is also might be in somewhat way related to the circuit disk depth, like the depth at which light is attenuated, right? So here, of course, you might be getting an average of, let's say, 20 meters, and here you're getting an average of maybe 1 meter. So the more material you have, the less like penetration depth of light. The interactions are dependent on like the depth at which light can travel within the water column. Does that answer your question, or? I hope that answers the question. Okay. Okay, wonderful. So there is no fixed depth. It just depends on the water clarity. So just consider this. It's a relation. It's related to water clarity, the depth at which remote sensing is conducted. So it's the surface layers, but depending on water clarity. So an extension of that figure here, there is also a value, or like the cost at the end user, right? If you're going to be going out at sea, taking measurements, chartering a ship, and buying fuel, paying for people, of course it will be very high. It's expensive, right? It's expensive, but it's needed because we need to validate the information we're getting from satellites, right? So a satellite is in space. Yes, of course, they cost just a rough figure. Maybe a satellite to be launched might cost whatever agency is going to deal with it. Let's say European Space Agency, they might invest 400 million, but then at the end user, the person who's going to use the data, right? You get information from tens to hundreds to thousands of square kilometers. That's information you collect. And then the cost for each user will be very low. But then if you're going out at sea, there's another question. Let me just finish up. Okay, let me try to answer the question. Please talk about corrections, if any, for running water versus still water. Please talk about corrections, if any. I'm not sure I understand the question. Maybe I'm not sure I understand this question. Like, what do you mean about corrections, if any, of running water? maybe try to rephrase the question. I'm not sure I understand the question here. I'll wait for that, or maybe, and in regards to the effects of waves, there are different, so the question related to depth up to which it was able to make the measurements. Well, not really. You can infer, can do some calculations to try to say like, well, light was available up to this depth. If you don't have Secchi measurements, then of course you can do some calculations, but these are, they'll come with uncertainties because they are based on empirical studies. But of course you can always try to figure out the depth at which light, unless you use other sensors. There are different types of sensors where you can get bathymetry, the depth at which, the surface is, but in terms of light, you can only infer like the information related on measurements you take of remote sensing. So again, back to this slide, the cost when you're using satellite or airborne campaigns at the end user, because of the aerial coverage you have or the wide spatial coverage you have, is relatively low compared to if you're going to use a ship to get, of course, most accurate, like the number of parameters you get when you're doing sampling of water samples and grab samples. They are very high. You get point samples, very low spatial coverage, but then the cost is very high in terms of like resources needed to do such work. There was a question yesterday when someone asked about things being coordinated, well, people are doing science, this country is working on this more or less the same things, but maybe they are just dealing with their own country or so. And for ocean color remote sensing, there is an international ocean color coordinating group. This committee or like group of representatives or experts, they have brought together different space agencies. You can see here you have European Space Agency, the Japanese Space Agency, you have NOAA, you have NASA, you have CSIRO from Australia, you have ISRO from India, you have like European Commission, you have the Canadians, and many more other agencies are brought together. So what they aim to do is to do training and capacity building activities. They liaise with different other agencies. They have scientific working groups trying to coordinate and standardize ways we do ocean color. And they are also a member of CEOS. And you have an international project office. There's a question? Oh, okay, no question, okay. And they have like a set of nice, well-prepared, like IOCCG reports. So if you are interested, I highly recommend looking at their page. I think it comes, so they are working on standards, trying to coordinate activities and collaborations, and the website is here. I'll give you a few seconds if you want to copy it down. So the main goal of IOCCG is promoting the application of remotely sensed ocean color and inland water radiometric data across all aquatic environments. So this is covering the open ocean. You have lakes, people working on lakes, you have people working on rivers, you have people working on coastal areas, you have people working on deltas. So through the coordination and training, so there are training activities that are coordinated by the IOCCG on use of satellite data or its use of instrumentation that is handheld or different types of instrumentation, right? And then they also try to connect the data providers, which is space agencies, or it could be commercial companies, and the users. So it could be us, the scientists, it could be policymakers, it could be managers for lakes or rivers. And they also try to advocate for different ways to make ocean color like one of the tools that supports, like decision making and provision of expert advice. One good thing, maybe of interest to some of the audience, it's, what I try to say is the IOCCG is like a one-stop shop where you have so many resources in the field of ocean color. If you're going to be doing remote sensing, I highly recommend you look at their website. And for people who are just finishing maybe their master's or even their bachelor, you might find some people posting positions for master studies. PhD positions, even postdocs, and even other like related topics or related job opportunities for professorships or just scientists or technicians. So have a look at their website. The link is here. If I'll give you a few seconds if you want to write it down. So job opportunities, and then of course, if you are interested in workshops and conferences, so some of the workshops you have training on how to use instrumentation, or it could be like dedicated conferences that are dealing with remote sensing. So here, this is planned for, some of the activities that have, well, these already passed, but like in 2021, they had a couple of them. These were run, some of them online, excuse me. And this was the Oslo Aquatic, so different activities. So just go on their website, go through different links and try to see what is available. That might be useful to your study or your work. Okay, so now slowly going into more like the remote sensing part. This is something you might hear people talking about. These are not fancy words, please. Just note, these are not fancy words, these are just simple words. When people are talking about multispectral remote sensing, it's just you're trying to measure light at a limited number of points, right? Spectral wavebands. So, to give you an example, if you're going to measure solar irradiance, the light coming from the sun and from all different angles, you can measure it using a multispectral sensor, so the black lines, so you measure maybe at 400, 500, 600, 700 nanometers, right? But then this is multispectral, you have limited number of bands. So here I couldn't find good example. So this is an example I gave when I was I visited France. They have small markets called Marché, Franprix. You find very few products, But then if you go to a Kero Hypermercado, you can also find a lawnmower, you can find screwdriver, you can find screws, everything. So when you're talking of hyperspectral, you get more information, you get more products. So here, if you're going to measure at hyperspectral, you measure at very small steps. Here, for example, you have hundreds and hundreds of wavebands where you're collecting information, so you can identify changes happening. So if you look at this plot here, if you are interested in the different shapes happening in between 700 and 800, you cannot get that information if you just have data from 700 and 800. But you can get that information if you have a hyperspectral sensor that is measuring information in between. Does that make sense? Or I hope people understand. No comments? Okay, good. Okay, so when we are measuring the radiometric quantities of light, these are apparent optical properties. These are optical properties of light that depend both on the medium, so if it's in water or if it's in air, and the geometric structure, how you measure it, like if you're looking at an angle, or if you're looking at an angle like from the azimuth, depending where the sun is, and also depending where the sensor is looking at. So these sensors, they are passive. They need a light source. In most cases, when we are doing ocean color remote sensing, that is the sun, right? And in most cases, they work with less energy. So the instruments I have, maybe it was difficult to, but they are traceable standards. And in most cases, the calibration of these sensors to convert digital numbers. So most electrical instruments, they give you digital numbers, 0 to 1 or 0 to 256. If you want to convert that to geophysical values, let's say you want to measure radiance, which is amount of light at a given angle, you do some calibration using National Institutes of Standards and Technology. Well, standards, they have a way to measure these parameters to convert digital numbers to actual geophysical values. So the main instruments we use for ocean color, if you're going to do ocean color, you have a radiance meter. So here you're measuring light from all different angles. You have your radiance meter, you're mostly measuring light from a specific angle. And then sometimes you have a scalar irradiance meter, which here I've only seen it, I've never actually used it myself. You have light from all different angles, but then also from the lower angles. So it's the instruments I brought here. I had hoped I would show you, but yeah. So that's like the schematic of how the instrument works. And in the next slide, let me see. Let me just bring everything together. Okay. So the instrument, you have a bundle of optical fibers that are used to detect light. So the let's see. That is the end here, like where you have the detector here. And then you have a photodiode which will convert the light into current or voltage, a 256 channel photodiode, so you end up with the number 0 to 256. These are converted through calibration to units that mean something to you, like radians, amount of light per unit area. And then you have a holographic grid that is used to separate light into single color and allow the detection by the photodiode. And you also have a polychromata that is used to isolate light into the different wavebands, like from the green light to the blue light to the red light, so separation of the light. So here you have an example of a radiance meter. So this is an example of the instrument I have. This, you measure the light at a specific angle. So the amount of light per unit area per wavelength. So in most cases, you measure light in the visible from 400 to 700, but this instrument can cover from the UV to near infrared. And the idea here, don't worry about the equations. This is just trying to be fancy, but don't worry about the equation. So you have the detector, you have a filter, you have a diffuser and light baffles and collecting tube. Then you have light being collected at an angle. Similar with the radiance, you have a light you're measuring light from all different angles. So here you don't have the dependence to the amount of light to the angle. So here you have SR, steradian, that is the angle. And then here you don't have that dependence to the angle, right? So you have a diffuser that assumes light coming from all directions is the same. And then it filters, and then you have the detector. It turned into voltage, and then, like the electronics. Same concept with the, how do you call it? The scalar irradiance meter. Light from all different directions from the surface. Same thing, same concept. Detector, conversion into units that you understand, like radians or irradiance units. So when we are doing our measurements, ideally, like here's a conceptual light path. This is a simplified version of what is happening to light. Of course, like they are just photons flying all over the place, but we are trying to do some tracing of the photons. So you do your ocean color remote sensing in the sun. You have your light source. Light, well, here we simplify things, just trying to make it like one photon. So a photon comes to the ocean sea surface. There's refraction that is happening. You hit features on the sea surface, white caps or foam. You have what your sensor is going to measure. The one, if you're trying to do remote sensing reflectance, you have a set of 3 sensors. One that is measuring irradiance, the light that is coming in, the universal light. And then you also want to measure what's being bounced back by the sky. And then what is coming from the sea surface. So you are measuring the total water leaving radiance, that is the bulk signal of water leaving radiance, the information just from the water. In some cases, you might have some glitter. I'll show you examples of that. And then you also have sun glint, that is the light being reflected by the sky, and then that's bouncing back on the sea surface. And then you have sometimes, like as waves are breaking, you have white caps and foam. And you have the contribution of material in the water column, right? You remember I was telling you like what contributes to the color of the ocean, which is the whole idea of why we do ocean color remote sensing. The in-water processes, the main processes happening, that is absorption of light and scattering of light, right? the scattering material, that is the suspended mineral solids, and the phytoplankton or chlorophyll, what we term as chlorophyll A. But then absorbing material, you have the dissolved organic material, you have the phytoplankton, and you have the mineral solids, right? So that's how we conceptualize things. Then we are measuring it in angle, the different angles here. So when you are doing remote sensing from a ship, in most cases, one of the biggest challenges is sometimes you are looking in the sun, because a ship is a mobile platform. It's always moving around, drifting due to winds and waves. So you're either looking in sun glint or glitter, or some foam that is formed, like when the ship is moving, white caps. And then, in some cases you could be looking at the ship shadow. So sensor geometry is always difficult because the ship is always moving. Ideally, you're supposed to be away from the sun relative azimuth angle. That is, when you're looking at the horizon, you're supposed to be 90 to 135 degrees away. And in some cases, meteorological conditions, it's not ideal to be doing ship remote sensing when it's raining or when you have clouds. From a ship, it's easier when you have clouds, they don't affect you, but if you're going to use satellites, then you have a problem, because in most cases for optical measurements, you cannot really see through clouds. If you also have ice or snow or rain, this is not ideal for remote sensing. So here you have the examples of sea surface conditions like glitter and shadow, waves, bubbles. So as I was saying, ice, snow, in one of the cruises I was on, we had a challenge of sea spray, due to big waves. And then also when you have the big waves, the temperature was very cold. So the water was freezing on the sensors. So in the end, you don't get any data because it's just you're looking at ice and your sensors are being clogged by ice. So you cannot really get information about the ocean. So ideally, these conditions are not ideal for doing any measurements. So an overview of what you normally do when you're doing ocean color, like essential climate variables. On board, you try to collect in situ measurements of chlorophyll A, CDOM, Secchi disk depth, salinity, suspended mineral solids, right? And then you're also doing remote sensing, because you would end up wanting to develop algorithms like relationships of the remote sensing measurements to what is actually in the water column, what is causing the color to change. And additional data, you remember I was talking about who, what, where, when. It is very important to know the location and to note down things that happen during your experiments. So cloud cover, wind speed, the direction of the ship, and the time. So that you can be able to link the ocean color observations to the station data you collect. So remember, write down things, note things down, and so that you can always link things and synchronize information. So when you take your measurements of remote radiometric quantities, you have your two sensors. I'll show you examples. You measure what is coming from the sky, what is coming from the sea surface, and the angles you measure at are from different studies. It has been shown that if you take measurements between 30 to 50, it should be okay. There's no fixed value, because in the end, you will normalize everything to what is coming in. So you will remove the dependence of your observations to angle, because once you divide everything by incoming light and then you apply a value pi, then you don't have your remote sensing reflectance value would be unitless, right? So what you want to do is what you want to get at the end of the day is water leaving radiance, like the information, like you want to separate the light signal here. You want to remain with water leaving radiance after you remove these other parameters, right? How do you remove them? That is a process typically known as surface reflected glint correction. So that means you remove a percentage of the signal. You assume, in most cases, it's 0.021. Like you assume about 2% of light that is in the sky observed measurement, is contributing to the total, like the bulk signal you're measuring. You remember LT? So your LT here is what the sensor is observing, right? Your sensor is observing the bulk signal. And from that bulk signal, you try to estimate these values. So this is an estimation. So here you see practical representation is, it is the best approximation, because identifying or quantifying these values up to now has been very difficult for the community, right? Of course, people are developing different ways to do it, but these values are really challenging to collect because it's just nature. So, and then you remove also the contribution by sun glitter, you know, like the specular refraction from the sea surface, and then you have the contribution of the white caps and foam and bubbles. But so this is theoretical. Like you remember, I was talking about theory and then actual data collection. So what is practical is, in most studies, you remove from the total signal just a small percentage, as I said, 0.021 multiplied by the amount of light that is being received from the sun. And then that's how you do your calculation. Then once you have your LW, you normalize it to the incoming light, and then you end up with remote sensing reflectance. Any questions so far? Sorry. No questions? No, this one I didn't understand. Yeah. Okay. So no questions so far? People understand? Wonderful. So, practical. How does it really look like? So these are just examples of different setups we've had over the years. So this is how your incoming solar irradiance sensor would be faced. It's facing straight upwards, and then you have one sensor looking at this sky, and then you have one looking at the sea surface. Same here, one is looking at the sea surface, sky, and irradiance. So in some cases, due to like how you can set up, the instruments might be a bit spaced apart, but ideally you'd want them combined together so that, you know, like you're getting information from more or less the same region of the sky or the sea surface, and as well from the same area. And yeah, just to showcase, we had one of our experts as well setting up the instruments. We did a similar study in the Lake Victoria here recently in October. And here you can see like the same setup. You have one instrument which is looking at the sky, and one is looking at the sea surface, and then you have one looking straight up into the measuring irradiance, the amount of light just coming in from the sun. So the setup is quite simple. You connect your cables, and you have an instrument that is combining all the data. And right, okay, yeah, that was and whoa, so with the setup, here is another example on a different chip, and how the data looks like after you do. Here are some approaches of how you correct the data. They have different assumptions, they use small different values. So you notice, like in most cases, the shape, if you look at the signal, the shape is the same, but it's just the magnitude. So the amount of correction they do to remove the unwanted, or more or less like unwanted signal, is slightly different, right? I hope that is clear here. No questions, okay. So the setup, again, here showing the whole setup. In one approach, you know, you remember I was talking about if you are going to be out at sea for a long time, it's always difficult to know in some scenarios what the time you're collecting data, because you have a timestamp. Now you can combine these measurements with images. So you take an image of the sky and the sea surface. Then when you're doing your correction, you can try to see if you really need to account for so much reflection from the sky or from the sea surface, if you had different contamination from white caps or foam or breaking waves. So the advantage of having a camera system to these measurements, you can try to figure out also like the area coverage you have measured your observations, right? And with this setup, we also noticed, like whenever you have sun glint in the images, the signal you observe is relatively high in the infrared range. So like starting from 600 nanometers going all the way to 950, compared to when you have nice like sea calm conditions, you would have a signal that is, you have low signal towards the near infrared, which is expected. Another example here, what we were trying to understand is the influence of measuring, like looking at the sky or the sea surface at different angles. You remember I said it is recommended to do the measurements at 30 to 50 degrees. Let me see. Yeah, so in this, you see like the observations have to be, well, if you're going to do 30 degrees, it has to be the same for the sea surface and the sky, right? You want to be measuring at the same angle. So here, this was the experiment. We wanted to see if the values we observe, if we have one irradiance sensor here, centered here, and if we look at different angles, right? And this experiment, the results are still ongoing, but well, I cannot say if there are large differences or small differences, because the processing of the data is still ongoing. But this is one of the studies. And one other setup we came up with the camera system. Here you observe you have a camera system where you are looking at different angles away from the sun. So here we had one sensor which was looking in the sun. So if the ship is moving, it's always difficult to change the direction of the ship because you have to reach a certain station. But in some cases, you always have one sensor. In this setup, we discovered that you would have one sensor which is looking away from the sun, which is what ideally the good measurement, right? So here you have one sensor looking on the left and one looking at the right. What you observe you see the value of taking pictures. You can see that if you are looking in the sun glint, your measurements, you would have higher values compared, you see starboard side and port side, right? So the green side, that's where your left side, you're looking at the less sun glint affected area. Your signal is lower, and when you're looking in the sun direction, your signal is higher, as you can see here in the different observations. So here, these are different way approaches to calculate the remote sensing reflectance. And with the different approaches, of course, you see different differences in the data. Here is a similar setup with the sensors looking in different directions, but just here, more simplified setup where you have 3 radiometers on this side and 3 here you have 4 radiometers, like radiance, and then 1 looking upward, and here you have 2 looking upward for each set. There are other approaches that have been proposed to collect remote sensing data. So you only need 1 irradiance sensor and 1 radiance sensor, right? You don't have to account for the sunlight, because what you do is, if you look closely to this schematic, you put your sensor, the radiance sensor, which is supposed to be looking at the sea surface. Now, in your in this, you remember the signal. If you are looking at the water surface from above water, you have a total signal that is combining possibly sun glint, sky glint, white caps, and you're only interested in water leaving radiance. So what this approach assumes is when you have a cover over your radiance sensor and it's just near the sea surface where you have the air-sea interface, the signal you're going to get is only the signal you are interested in, that is the water leaving radiance, the information from the water column, right? So in this schematic here, that's more like, more practical view, where this is the version from 2006 and it was improved over the years. So this is like the 2019 version where you have a black surface, so that means you have less interaction with the environment. The signal you're getting, you make the assumption that it is only coming from the water. So you have here the irradiance sensor, it's looking upward, and then you have a camera system to also take images of what's happening in the water column, and then you have your radiance sensor. So you simply divide your water leaving radiance because it has ideally less contamination from whitecaps, foam, or bubbles, and then you get your remote sensing reflectance. So here you have a floating device, so it's just floating at the sea surface, as you can see in this image. And well, also with this setup, you can add other instrumentation if you're interested in collecting maybe salinity or temperature information. Yeah, one other instrument that we have been using over the years. So this is our torpedo. It's more, well, the right word is a free-falling profiler. It's similar to, the setup here is similar. You have a radiance and irradiance sensor. And now, the only missing thing is the cap. Why? Because you do measurements in the water column. Ideally, you profile your measurements in the water column, and well, you can do free falling up to, I don't know, it depends what you want. But in most cases, because you're doing this from the hull, from the back of the ship, one thing you do is before you get to a station, before you're doing your station observations, you slowly release it, and then you let it away from the ship, like you pull it, so it will be floating at the sea surface. You let it go for about 20 to 50 meters. The reason why you do it is you don't want it to end up being entangled with the propeller. So you let it go 20 to 50 meters, and you don't want your measurements to be affected also by the ship, or like, well, the propeller moves things around, so you want it to be measuring like, well, the expected environment that is undisturbed. Of course, yeah, there's some level of disturbance, of course, but we assume after releasing it after some time, 20 to 50 meters, the observations we get are next to clean, or rather undisturbed. And then what it simply does here in front, you see it's more like a torpedo, it has a weight. So that means once you have had it 20 to 50 meters, you let it free fall, it will just, it falls into, like, it just takes measurements within the water column. It also has like a backscattering instrument here. Here's the radiance measurements from the water, and then also what is coming in from the top, right? And then you can always do like inversion approaches where you can convert the in-water measurements to above water. There are some calculations you can do. So we have been talking about apparent optical properties. These depend on the angle and the medium you're measuring in, right? Now these inherent optical properties, these are optical properties that depend only on the medium and are independent of the light geometry, right? So these sensors, they have a light source, can resolve high variability, directly measure optical coefficients. So you end up measuring absorption coefficient, scattering coefficient, attenuation, beam attenuation. And one of, like here, I just tried to give an example of one of the key instruments that has been used in the community to obtain beam attenuation and absorption coefficient, right? So yeah, here just to give you an idea of the instrument, it's probably, I think it's about 1 meter, just less than 1 meter length. So you have a battery inside, and then you also have a light. You have a light source and detector end. So here, when you're measuring beam attenuation, like the walls are non-reflective because you want to measure the loss of light in between from the sensor, like from your light source to the end, right? So that's why you have non-reflective walls. You just want to measure the light that is transmitted through the water volume. And the absorption tube here, you have reflective walls. You really want to measure how much light is absorbed within the sample volume. So these depend on the medium and are independent of light source. And here is a nice schematic that explains what happens, like when light hits a particle, right? So you have your particle, you have your light source, incident light coming from the sun, light coming from your light source, or maybe you have a lamp. Either the light is absorbed by the particle. It doesn't, well, if it's absorbed, it means like, well, the light is not going to pass through, right? if it's transparent, then of course the light is unscattered. It just goes straight through the particle. Or it's scattered backward. It can either be scattered backward. It can be scattered forward. So that means some of the light could be absorbed, and then some of it might be scattered forward, like it will be transmitted forward, right? So you have scattering, absorption, and attenuation, the loss of light. Well, that is also related to the absorption, right? And in the ocean, what materials scatter light in natural waters? Salts. You have the water itself. You have inorganic particles. And here is an example of like algae or organic particles that scatter light also in the ocean. Then, of course, you have bubbles that form in the water column. Beam attenuation coefficient. Don't worry much about the equations. Okay, there's a question. Please, how do you mark out points of interest of water? Oh, good question from Brian about marking locations on water. Yes, of course, that is that's a very good question. Like, so ideally, when you are doing studies at sea or even on land, you are supposed to have a GPS, and in most cases, the measurements from the GPS or like they should be logged automatically. So in some cases, in most cases, every minute. So you remember I was talking about whenever you go to a site or when you're taking measurements, you record the time and the location. So the best thing is always to record things in UTC. Why record things in UTC? Then people will not ask the question like, was this done if things are done in Uganda, and someone who's going to look at the data in, for example, let's say the person is in Hawaii, which is about 12 or 13 hours behind, then that means if you took your measurement at 8 a.m. in the morning, for someone in Hawaii, that is a different time. So ideally, that's why we do things at UTC. And you collect measurements with the GPS. So if you have your GPS, you have your time stamp, you have your date stamp, and then when you take your notes, you know the time and the location. That's how you always know where observations were conducted. Any other question or? Okay, so I'll continue. I hope I answered the question about location. So we are talking about beam attenuation. So you remember I was saying beam attenuation is just the amount of light that is lost when light is passing through an object or material. So you have your light source, you have a sensor which is measuring how much light is reaching it. So whatever is lost in between is what you consider as beam attenuation. So you have your light source, light passes through like a volume of, it could be water or it could be glass or material. So you know that the distance between your light source to the sensor, then you can estimate a coefficient of how much light is lost per unit area, per unit distance. Same thing with chlorophyll. You have your sunlight. What happens to the light? It's either absorbed by chlorophyll, the energy. So here on your axis, you have the energy, you have your ground state for emission, you have emission here. So here's emission. You absorb mostly in the blue, right? Which is around 400 nanometers, 440, I can't remember, around 414 or 412. And then you have fluorescence. That's one of the parameters you can measure of chlorophyll, which is around 670 or 660. You also have heat loss, like it's a ground state. You provide energy, it's absorbed. Some of it is emitted as fluorescence. Absorption of the red light also that happens here. Right, makes sense? Emission? Any questions? No? Okay, so one of the IOPs, again, turbidity, you measure the scattering properties. Remember I was talking about scattering, so you measure the scattered light because turbidity is mostly a measurement of like the dissolved, not the dissolved material, but rather of the particulate material that is, influencing the clarity of water. So that's why you measure scattering of light, because the light is bouncing off the material. So remember, here you measure backward. So some instruments are measuring the backward or the forward scattered light from the instrument. Yeah, we have 7. Before I go into this, any questions? I would rather have questions than to continue. I think for today we have, how do I see questions? Chat. Any questions? No questions? Okay, so we'll continue. Yeah, just I'll try to quickly go through one of the parameters we talked about. You remember we said in the water what causes the different colors. Let me just try to see if I can get that image I had. So there is color dissolved organic material, you have phytoplankton, you have suspended solids in the water column. So now I'm going to try to just give a brief introduction onto the color dissolved organic material. So sedum, color dissolved organic, that's the yellow substance. The German word is Gelbstoff or Gilvin. The colored or chromophoric dissolved organic material, that is material that passes through a 0.2 micron filter. So practically or technically, it has assumed that when you filter your water through a 0.2 micron filter, you're not supposed, well, ideally you're not supposed to have any solid or particulate material passing through the filter, but sometimes in some cases you have very micro colloids, like very small materials, but the filters in an ideal scenario, it's supposed to have just a fluid, which is the dissolved organic material. And this is optically active portion of dissolved organic material. And it absorbs light in the ultraviolet and the green spectrum. So mostly here, that's where you have very high absorption of light. And then here, once you go into the near infrared, there isn't much activity. So as it absorbs light in the UV and green spectrum, it is assumed that it shields most of the microorganisms from strong UV light. That means, like it's a good protector for some microorganisms or like, how do you say, corals. So presence of sedum in areas where you have corals or certain microorganisms is very good. And it also protects some of the microorganisms that photosynthesize, right? And in most cases, it can be used to trace water masses in coastal areas. How can you trace water masses in coastal areas? It's a simple relationship you have between sedum and salinity. Very low salinity waters or fresh waters tend to have a high concentration of sedum because it is drained from the land, or it also is, how do you say? It is made from drying algal material. So it also is, it contains a pool of dissolved organic carbon in the ocean or water column. So going to the point where we said it's related, it can be a tracer. If you look at the rivers and estuarine systems or coastal waters, where you have high concentration of sedum, which is the X, you have low salinity. Like in rivers, of course you have brackish waters, but in rivers or in freshwater systems, you likely find that you have high concentration of sedum. But once you go into the open ocean, you have very low concentrations, and then of course you have high salinity. That's the relationship that that links them. So here you have a conservative behavior. That means high concentration of sedum, you are likely going to have low salinity that is in the fresh water. That is the source. And then once you go to the sinks, that is microbiodegradation, photobleaching, that is in the open ocean. Here is just an example of an instrument we use to spectrophotometer to obtain like absorbance and fluorescence measurements. So example of sedum is T, right? Yeah, well. So why do we filter? We want to get the dissolved organic fraction. Here's just a few examples of what sedum looks like. It's mostly brownish, yellowish waters, coffee color. And then when you measure the absorbance, you have, like you remember we talked, it absorbs very high in the UV to green wavelength. You see that's why you have a curve like this. And it's 1/2 past. I think we can end here. Well, just an example of different concentrations in the world where you notice high concentrations are close to land, and when you go to the open ocean, it's very low. So you end up having that relationship of salinity increases towards the ocean, sedum decreases towards the ocean. Salinity decreases towards land, sedum increases towards land because you have more sources. And just one quick image I find interesting. It's one here is sea snot. It's called snot. It's just the snot from the sea. It has been happening in Turkey. So here's just a few satellite imagery of how it looks like from space. Thank you for listening, and thank you for the interesting questions. And the unanswered questions, please bring them back tomorrow. And I hope you enjoyed the lecture. Have a lovely evening.